Hello, good morning to everybody. So welcome to this Friday morning session of the conference. So today we will have the third and last lecture of Professor Pierre Rouchon. So please.
Okay, it's working, perfect. So good morning to everybody. So it is the last lecture, and it will be on quantum feedback. Okay. So from an engineering point of view, what we have seen here in all these things is that, in fact, all what you need is to apply and do computation with these rules. Schrödinger equation, collapse of a wave packet, where the outcome gives you the measurement, y, and the input, okay, is given by u, in general, in a controlled Schrödinger Hamiltonian, okay? So, and what you have to take into account is that when you have your system and you couple it to something that could be your controller or your measurement device, you have to use tensor product. Okay. So here you have yes, I start. I have to go to the last point because I start the beginning here. No. Voilà. I guess it's okay now. Yes. So you have two kinds of feedbacks. First kind of feedbacks is your system is like this. So what we have seen, we have all the equation to say that you have correlation between your input, classical input, your control input, and the measurement output. And here you have a stochastic master equation, okay, in between. And what you can try to do is based on the output measurements, you have typically, if you are looking for in fact, regulation problem, you have some reference, some goal, and you have here some computation or classical circuit, if you want, and then it gives you where you have a feedback scheme. So I will detail a little bit the feedback. So one of these feedback is just that u is a static function of y, okay, which is called a proportional or a static output feedback. It is called since the work of Weissman by Markovian feedback. Here in control engineering, the classical controllers are known, and most of the controllers are proportional, integral, and derivative controller. And in this case, in closed loop, you do not have a Lindblad master equation. You have something nonlinear which is very difficult to analyze, the convergence and so on, except when you have no memory in the controller and you have just depends directly on y, which is called Markovian feedback. And in this case, we have a Markovian, a closed loop Markovian dynamics Lindblad equation. And if you do typically so your system is a nonlinear hidden state stochastic system, okay? So you can use some Lyapunov state feedback, and you have many open issues on this. So here you have this paper 20 years ago is a nice paper. It is related to quantum error correction. You have also this paper of Maziar Miramini and Ramon Van Endel when Maziar was visiting Caltech. And you have also in Paris the group around Nina Amini who was exploring, in fact, a quantum state feedback. So I will also discuss this. So to do this, what we have, and I summarize all the lecture before in discrete time, okay? It is this thing. So remember, you have, in fact, a Krauss map, which is this one, okay? It is decomposed as, in fact, so here it is a quantum channel, here it is a Krauss map, okay? Dependence of a measurement outcome, so you have a sort of decomposition, sum of different sub-Krauss map, and your dynamics is represented just by this. If you detect Y, you have to update rho only by using this part of a Krauss of a quantum channel. You divide by the trace because the trace is less than 1, and the probability to detect Y knowing rho and U, it is this. So everything is here. Okay, the structure is there. Okay, and you can use this structure, in fact, to analyze closed loop things. So I will detail this after that. So this is the first part. It is called the measurement-based feedback. Okay, the controller is classical object, and you may also assume, in fact, that the controller is also a quantum object. If you want to achieve convergence, you need some irreversible process. So you assume that your controller is a dissipative quantum system. You have decoherence in the controller. And typically, if you go back to how to use the decoherence in the controller to stabilize your system by some coupling, if you look at in physics, it's go back to optical pumping, okay, of Alfred Kassler, and also it is known also in physics, typical this kind of coherent population trapping, okay? It is something like this. And you have also, of course, in fact, dissipation, what is called also in physics, dissipation engineering, autonomous feedback, and so on. So you have, and here you have typically from system theory, you have what is called the SLH theory. It comes essentially from quantum optics that has been, in fact, pushed by Mabuchi and also John Gauff, okay, James Peterson and colleague from Australian and also Japanese school, okay. The stability analysis of this kind of stuff, it is a big Lindblad equation, okay? And you have to stabilize this. And last point, this thing, in fact, you go back, in fact, to what is called the Watt governor, where a mechanical system controls another mechanical system, okay? It's purely analog, okay? But it is at a quantum level. Okay. And what are, in fact, typically the techniques that are behind this? So it is typically this. So you have your system. If you try to do some big picture of that, you have your controller. You are in the tensor product. So you have a Hamiltonian of your system, the Hamiltonian of a controller. You have an interaction Hamiltonian. It is the way that you can do how to design typical interaction Hamiltonian. In general, you have few decoherence on your system. Much more decoherence on the controller, of course. And typically, what you want to do is to stabilize typically the ground state manifold of the Hamiltonian of the system, typically. So you neglect this kind of thing that becomes noise. Typically, it is in autonomous quantum error correction. This comes from noise, okay, in your system. You know that you encode this in the ground state of an Hamiltonian, okay? And you want, in fact, to find some realistic, and realistic is important here, coupling Hamiltonian and decoherence in the controller, such that, in fact, you protect the quantum information stored in the ground level of the system Hamiltonian, in fact, in an efficient way. And here, what you have a lot of time scale. You have, in general, averaging, so rotating approximation and so on. In general, the Hamiltonian, in fact, is dominate the dissipation error. So you have a gap, okay? You are protected by a gap, but it is not sufficient. Here, the same for the controller. And you assume that the decoherence here is dominate the decoherence that you have here. And all these things, you need a lot of techniques to analyze what's going on in this composite system here, this model reduction, and what is called adiabatic elimination, singular, regular perturbation, and so on. So I will not enter into the detail, but it is a difficult problem in general, this thing. Okay. So I will first focus on measurement-based feedback with, in fact, several typical controllers. So first is something obvious. Assume that, in fact, your system, so the control is first you measure, okay? And then your control is just a unitary pulse on your system, and you can choose typically the amplitude of this pulse, okay? So you know that you first measure, and then you control. And if you assume that your control is just a static function of a measurement outcome, then you see that the closed loop dynamics read like this. So it is a new Krauss map. So you have the open loop Krauss map, okay? K, which is the sum of Ky, you see here. And you have a closed loop Krauss map where, in fact, you add U, okay? In these things, I assume that open loop Krauss map is with U is equal to 0, typically, and I do nothing, okay? I just measure. And of course, you can change your dynamics just by what is called Markovian feedback, okay? So in control engineering, it is called static output feedback. U is a static function of a measurement. So something, it is in the PID controller, it's the proportional part of a feedback scheme, you see. So you can do this, of course, exactly the same scheme, but for typically diffusive system. For diffusive system, you have here, I take here the simplest, a very simple case, where in fact, I have a qubit, okay? And what I measure is the fluorescence of a qubit in a diffusive way, okay? So in this case, I have, in fact, the evolution of my system here due to the measurement with the measurement back action. So you have the noise, you have here the detection dy, and here, just after the measurement outcome, okay, dy, I assume that I adjust u, okay, by this proportional feedback law, okay, something very basic. So which means that in this case, in fact, I have to use this thing in this equation here, okay? So in open loop, when you put u is equal to 0, gain, the feedback gain is 0. What you have this, in fact, in average master equation, and you know that if you have some disexcitation of a qubit, you always go down to G. So your system globally converges to the ground state. And the goal, in fact, of a control is, in fact, to maintain your system in an excited state. And since it is clear that since you measure the fluorescence, you can send back the photon, okay, that you measure in your device, okay? It's something as if you put a mirror, okay? So if you do this, of course, what you need in this case, since I am in the Ito case, I have to take the Ito correction, which is this one. So here you have typically the asymptotic expansion of the exponential, and I need to take into account some second order terms that gives you this term here, okay, and this term. Okay. And then I put this back into, in fact, the master equation, and here are, in fact, the outcome, the result of the computation. So if you want to have how to do this, you have this in the lecture note. In the general case, when you have an arbitrary number of measurement and an arbitrary number of control like this, what is interesting is that when eta, the detection efficiency is 1, so perfect case, and if you adjust correctly the gain, okay, which is in fact minus the square root of kappa. Kappa is the measurement strength, okay, measurement rate. Then you get in this, in fact, Lindblad equation, stochastic master equation. Here you get, in general, 2 decoherence operator, but you get, the second one is 0, and the first one is sigma plus, which means that in closed loop, what you have done, if you have changed sigma minus by sigma plus. So you stabilize E. So it is something simple here, and you can look, in fact, at the experiment of Benjamin Huard. I guess that next week he will speak a little bit of that. Here, I assume that I have homodyne detection, but if I use heterodyne detection, okay, I can do the same thing, but here, you see, I use only one control around sigma y, but also I can also use control on sigma x, and it is a MIMO case, and with Philippe Compagne, they have done, in fact, such kind of feedback scheme in an experiment. So, okay. For superconducting circuit. Yeah.
Without the control, it would have gone to the ground state.
Ground state.
And now with the control, it goes to the...
Yes, in the perfect case.
And, but could I change the control so that it goes to some superposition?
No. It's in closed loop, you stabilize the excited state. In this case.
In this case, but can I change the control in some way that I go to some other desired state?
Yes, you can use, but yes, of course. You can typically, you can put additional sigma x, okay, and choose things to try to stabilize over state. So I do not consider this, but it could be interesting, okay. But look at the paper here, it is there, okay. So this is the first feedback scheme. So it is Markovian feedback. Okay, so you understand, and it is quite. It could be very useful because it is very simple, and to realize this, you don't need a lot of computational resource. Okay, in the controller. Here it is an idea. So it is. It corresponds to it is made 30 years ago. Same group is how to use. You remember, so the quantum non-demolition measurement of photon, it is based on this, in fact, Krauss operator, the cosine and the sine of the photon number n, and you can, just by, in fact, changing the parameter, typically here, choose u and v, okay, as a parameter that you can change, in fact, as you want. Okay, so it is 2 control inputs. And of course, what you want to do is to do some feedback scheme. So at step K, you can change U and V and look at this Markov chain here. And Y is something which is E and G, so binary response. And if you assume, so in this scheme, what you get is after each passage of an atom, you get 1 byte of information, 1 bit of information. So if you want to encode, in fact, a number of photons between 0 and 2m minus 1, 2 power m minus 1, you need m bit of information. So which means that in this procedure, what you can do, can I measure any state in this range with only m, in fact, atoms. And here it is, so I show you the feedback scheme. The feedback scheme is this. So you have this, in fact, update, and at each time step k, you use uk and vk depends on the past measurement. So it is a feedback scheme, but it is not Markovian feedback. Okay? You have to store all the initial y0 until y minus k minus 1. Here you have this function f, it is j, it is 0, it is 1, and you use this thing. So I will not detail this. I have a small simulation which is very, very simple. And at the end, you converge to a Fock state of value n, which is exactly this in this case. So at each time step, you see, you get one bit of information corresponding to the decomposition in base 2 of a photon number, okay, with this thing. So I have a small MATLAB simulation which explains you how it works. So I have encoded this and maybe. So I will start from, in fact, so I will just detail this. So you see? So I will detail this thing. So it is just one realization. So here I assume that I have a photon number, so m is equal to 4. So either I have 0 up to 15 photons, 2 power 4 minus 1. Here I take as initial state a coherent state of amplitude around 6 photons, okay? And what you see is that at each time step, I have a processus of decimation process. Here, you see, I have this thing, and the first measure tells me that for all, in fact, yes, it is odd number, even number, I have to put 0. And I keep just, in fact, the photon number, which is even. So I have a sort of dissimulation of a photon up to this. And then, okay, and I have to, in fact, of course, to renormalize, okay? And then you continue. When you continue, you have to do this, but in fact, you only keep, so you keep here on these things 1/2 of a bar, and then you continue to keep 1/2 of a bar by adjusting the things here. So at the end, we keep this one, and this one after. So 1 atom, 2 atoms, okay? And 3 atoms, I only have something, I don't know if it is this one or this one. And at the end, it is this one. So it's a decimation process. So for this, just you in fact adjust the phase in the cosine, okay, and the dephasing per photon, okay. It is just this. So it is a nice thing, and you can do this. So I will do another. Let's do this in another realization. And you have on my web page, in fact, yes, here you have another realization. So you see, you have this, so you continue. At the end, either you don't know if you have only 1 photon, or if you have, here it is 9 photons, okay? And you have to do, and at the end you get this one, okay? You see, it's a very clever thing, but the problem of these things is that if you have an error, then you go to the bad things, okay? So it is not very robust, in fact, to measurements error and so on. So an issue will be how to, in fact, robustify this ideal scheme, okay? If you have noise, of course, this process is very sensitive to noise. Okay. Yeah. So you see that V, the dephasing per photon, decrease at each time by 2. You start with pi over 2, then pi over 4, pi over 8, and so on here. And you adjust the phase, in fact, to have 0 and 1, 0 and 1 at the good location. It's a trick. Okay. And then I will speak on these things. So I will detail a little bit these things. It was the first, in fact, experimental realization of a true quantum state feedback. So you remember it was at the initial state. So I guess that, hope that the animation will work. Yes, I hope so. I remember this. Yeah. So it is this, and then you close loop with a real-time computer, okay? And then you continue and so on. And the goal is to stabilize a precise number of photons inside the cavity, okay? And for that, what you have, this is the actuator, what this is. This is the sensor and this is the actuator. But look, the actuator is a coherent pulse. So you are on the diagonal in the Fox basis, okay? If you put a coherent pulse on a diagonal state, you obtain off-diagonal element, okay? This thing. And it is, the controller is a little bit, the actuator is a little bit tricky, not very well adapted to the goal, but it was possible to do something. Okay. So I will detail a little bit the structure of a quantum state feedback here. And then, yes. So what you have here, so I take the simplest case. So it is always the same thing. So you have M, ME and MG with this thing. You have, in fact, the ideal case here, and here you have the actuator, okay, which is just a coherent displacement. So the input is U, the state is rho, and the output is Y, okay? So in the ideal case. So I will draw a picture of a structure of a feedback scheme. So you have your system here. So it is here, it is the cavity. Okay? It is S. So here it is the quantum world. And here U is my control. And Y is what I have. So first, what I want. So the state here is rho. Okay? So I have a box here that compute rho. It is typically a state feedback, so it is F. Okay? But here rho, I do not have rho. I have an estimate. Let's set E. Estimate. And F estimate. Because I do not measure rho. It is a hidden state. Okay? So I have this. But I have what is the estimate? The estimate will be like this. I will take the past control, U. I will take, in fact, here, the measurement Y. I have a block, what is called a quantum filter, that give me outside the block, au chapeau, and I close the loop. Like this. Okay? So it is, here it is the controller, and here it is what is called the observer. So it is an observer-controller structure. Okay? From your past measurement and your past control, you estimate where you are. It is here. And here it is a quantum filter. What is the quantum filter? So here, you know what I have. Typically, I have rho k plus 1 is equal to my Krauss map, yk, uk, and rho k over the trace. Okay? This is this input-output relation through rho. Okay? What I have, my quantum filter is just this. It is rho k plus 1 at, it is equal to k. I know what is the measurement outcome. I know this. So this is the input of a quantum filter. But I use yk, uk, known signal. But here I have my estimate. And I divide, of course, by the trace, but not here. I divide by the trace of k, yk, uk, rho k. But here I divide by the trace yk, uk, and here, of course, it is rho k estimate. Okay? And then I close the loop by using that uk. So it is, I know what is rho k estimate. It is a function f, my feedback scheme, of rho k estimate. Okay? So what is written here is the equation. What is written here is what is called in control engineering block diagram scheme. So control engineer like this, but mathematician like this. Okay? So you can see exactly the same thing with two languages, either block language or this one. I prefer this one because it is much more compact and efficient. Anyway. Okay. So you see, and everything is here. So at each time step, yk, you measure this, you use the quantum state estimate, then you compute uk as a function of rho k and state. But the problem is that rho k you don't know. So you have to inject this part here. So, and now the design is such that. So this quantum filter, you have no choice. Okay? So the design, what is called a quantum filter. Yes, okay? This, it is a quantum filter. And you will have next next week, people are looking at convergence between of rho k estimate to rho k. Okay, what are the conditions of yk, uk, and so on? Okay, it's something that if your filter is converging. But the design is in two blocks. So the quantum filter is fixed, and you assume that in closed loop, so ideal closed loop, it means that you consider rho k plus 1, okay, I will say ideal, ideal, so I will kill this, and I have found f such that when I close the loop, here I have f of rho k, okay, over the trace, I assume that, so f such that rho k tends to rho bar, typically rank 1, okay, which correspond to the projector on your goal Fock state, when k. So you assume that you converge almost surely. So you have convergence. So it's the way you have a trick, you have find this, but you apply it on this. And you can prove that with this scheme, you always converge to rho bar. It is what is called the quantum separation principle. Yes? No, you just assume this. You have this ideal Markov chain, which means that in this case, if your initialization of rho is perfect, you have no distinction between this, and you are in this case, and it's okay. But if you assume that you have no information on rho, typically in quantum state preparation, okay, you want to prepare rho bar, what can you do? And in fact, this procedure always converges. Why is it convergent? Because in fact, there is a trick here. The trick is that in this scheme, the expectation value of rho k is a linear function of rho 0. What is the expectation value of rho k? Okay, knowing rho 0 and rho 0 estimate. It is just the sum of a different possibility, but here I have UK, okay? And UK is this. So it is the sum it is, yes, it is the so you have to write this, you can write this like this, or you can write this like this. You have always two. Your rho k plus 1 is equal to k, yk, uk, k, yk minus 1, uk minus 1, k, y0, u0, rho 0, over the trace of these big things. And the trace is the probability to have all these things. Okay? Is the probability to detect y. So, which means that when you take the sum, this is, in fact, the sum, okay, of all possibility that you have here of something which is, I will say, y0, u0, y, k minus 1, so like k plus 1, k, uk, okay, all possibility according to this rule, okay, when you fix yk, you have this thing, okay, only probability of this, of k of yk, uk, k, y0, u0, rho 0. So it is linear. And now, if you assume assumption that in fact the kernel of rho 0 hat is included in the kernel of rho 0, okay, what you have in this case is that you can always set that rho 0 is equal to gamma rho 0 plus 1 minus gamma rho 0, I will say C, for example, because for gamma small and positive, you see, because of that, rho 0 hat minus lambda rho 0 is positive. Okay? Because the inclusion of a kernel. Okay? And now I will consider this thing. I continue this way. The trick is this one. I will consider the estimation of the trace of rho k plus 1, rho bar. Okay? So, knowing, in fact, rho 0 hat, rho 0 hat. So, rho 0 is equal to rho 0 hat and rho 0 hat. Okay? This is valid for all rho 0. So it is something like this, and what it is? Since it depends on linearly on this part, okay? What it is lambda, expectation of the trace of rho k plus 1, rho bar, knowing what? Knowing that rho 0, lambda rho 0, and rho 0 hat. So I put lambda, okay? Here I replace this by lambda rho 0 plus 1 minus lambda rho 0 c plus 1 minus lambda, and here I have the expectation value of the trace of rho 0 k plus 1, rho bar, but I know something else. I know that I have here rho 0 c and rho 0 hat. This guy is less than 1, okay? This one is always less than 1, okay? I have a barycentric combination of these two things. And what I want to prove is when I start from rho 0 and rho 0 hat, this guy tends to 1. But I know that this guy tends to 1. So when I pass to the limit, okay, I know that this quantity converges to 1, and this quantity is a barycentric combination of two quantities that are between 0 and 1. So since this guy goes to 1, this guy goes to 1, and this guy goes to 1. Okay? So you have convergence because of this. Okay? This is called, so you can separate, which is nice. You don't care, you just consider the ideal case where you have the perfect knowledge of your initial state, and it is something interesting for preparation of quantum state. Okay? The problem here is first to find the good F and to prove that you converge. And for that, what we used here, it is this thing. So what is the trick? So I will detail a little bit the trick on that. It is clear that in open loop, okay, when u is equal to 0, you consider u equal to 0. And you try to find something which is conserved, martingale. And from an open loop martingale, you design a feedback scheme, but it becomes a closed loop super martingale, okay? So you know that for all function g of n, trace of g of n rho is a martingale. And now we will use this kind of martingale. I will draw a picture here. So it is n here, it is 0, 1. Assume that I want to stabilize to n bar, I continue. N bar plus 1, and so on. And what I have to do is to find a super martingale, and I will try to make this super martingale, here it is G, to converge to 0. So I will put 0 here for G, and here I will take something which is higher, so, and here I will take this, okay? And what was important in this case is here to look at the asymptotic that you can take for this kind of martingale, and it grows here as the 8 grows as the log of n, when n is large. You have to do this because you have coherent displacement which is not well adapted to your system. You are on the diagonal, not at the good photon state. You have to get outside the diagonal and then remeasure to concentrate. And if you want to remove heating, you need this thing. Otherwise, part of a trajectory in closed loop heats. And after that, what is F, the feedback law? It is just, you assume that you take the expectation value of Gn rho k plus 1. You say, knowing that rho k and uk is equal to u. You have something, and you consider the mean with respect to u of this, and the argument of this minimum, okay, it is f of rho k. Okay? You take the expectation value, it is a function of u, okay? Since you put u is equal to 0, it is constant, so you try to decrease it by taking the argument of a minimum of this, okay? And it is the way that the feedback scheme is designed on the Rouchon experiment, this way. But you need this. You can, in a first step, people say, well, I can use this kind of things, completely flat profile, since all these states are orthogonal. Okay, I can put this, 0, and this. But with this kind of Lyapunov function, okay, you can put it a martingale, this one, a super martingale. But the problem is you may know distinction between typically n is equal to 3 and if you are at n is equal to 10. When you want to go to 10 to 3, it is much, in fact, far than to go to 4 to 3. Okay, so you have to take this into account in the price, in the energy to go back to your system, to the goal state. Okay. So here it is here, and here maybe I can show you what's going on real data. It is a movie that has been, in fact, done by Igor Dotsenko. So to give you some idea, so the period is around 80 microseconds, okay? But the photon lifetime is much longer. So you have time, okay? Before, in fact, the mirror capture one photon, okay? So you have this, and here you have the imperfection. The detection efficiency is 40%, detection error 10%, and additionally, as shown here, so they send atoms, so one atoms leave the cavity when, in fact, you do not see the photon, and you, at this time, you send an atoms, okay? But in fact, you have a distance between the detector and the photon here, which means that in this setting, you have one atom here, 4 atoms that are between the cavity, that have interact with the cavity, but that are not yet detected. Okay? And then you detect it. So, in fact, what you have is this. If you try to you have this Markov chain. What I have, so, you know, my update is this. K, U, rho over the trace of K, U, rho. And here it is rho, K plus 1. So if I assume that at step K, okay, I measure, so here, I get yk here. So I will put yk here, okay? But, in fact, I will decide what is UK. Okay? No problem. I decide UK. But the UK that is here will be applied on which state here? It will be applied on the photon corresponding to atom K plus D, the delay. So what you have is this, K plus D, and here it is rho K plus D plus 1. So it is a little bit bizarre. But it is, if you take a shift, okay, the shift is this one. It is, so you take K plus D is equal to K tilde, okay? It is this. So I am at K, and here it is this one. And this one, yes, it is not exactly this. So the trick is to put the delay just on the control, in fact. So I missed something here. It is rho K plus 1 if with a K tilde. It is equal to K plus D. It is K of YK. Yes. So K was my actual time. Okay? Let's see. But now if I took that the physical time is this one. Okay? So I have this. Here it is the yes, it is K minus D, UK minus D, rho K over the trace. But there is something I missed. Here you have to put K here. So my here it is. Says you agree that the update of this guy, okay, should correspond to the measurement, okay, associated to the photon, okay, to this. So we see it is K plus D here in my things. If you look at how it works, so I missed something here. The collapse of rho K is associated to Y, associated to the same atoms. Okay? It is not the time, it is the good atoms. Okay? It's just a label. So it is as if you have a delay in the feedback loop. So with a delay, you say, well, no problem. I will take my feedback scheme. So feedback is, okay, UK is equal to F of rho K. So I will say so, okay. So what is it? UK is equal to F of rho K plus D. Well, but K is the actual time. So the only way to do this is to have an estimate of this guy, and you will say that rho K plus D, it is equal to the estimation of rho K plus D, so D, estimate, so to be causal, okay? Knowing what? Knowing rho K and knowing UK plus UK minus D and UK minus 1. So you predict in average, okay, what's going on this based on the fact that you have a delay. It is as if you trace over the atoms for the density operator, okay, that have interact with a cavity, but that are not yet detected. It is the way that you can interpret this prediction in average to synchronize the things, okay? Okay, so all these things. So spend a bit of time on that. But it is important. And now it is, so I will there is a small movie on this to see what's, because it is interesting to see after that what's going on. It seems that it is not so. So you see? So I will show that. So here, what you have is the detection here. So from time to time, you have no detection, and from time to time, you have two atoms passing through. So you have also this thing that you have to take into account. This is the Lyapunov. This is the martingale. This. Exactly this. This is, in a certain sense, the distance to the goal, free. And this is the control. So what you see here is that we start, here it is, at each time step, it is the density operator here, okay? And here it is just, in fact, it's diagonal, okay? And here you have a time here, and here it will change time to time. Okay, so you see a sequence. So you see here you have reached 3 photons, almost. So you do nothing. And here you have a switch. And to go back on the good position on the diagonal, you have to get outside the diagonal and so on. And it is clear that at different time, the different rows do not commute in this case. It is clear. So it is a very true quantum state feedback, where the quantum state at time t does not commute with the quantum state at time t prime, okay? Where t is different of t prime in general. Well, and what you see is that you maintain, okay, your system close to free, and it takes you through the filter to recognize that you have lost 1 photon, and then you re-inject through a current pulse, in fact, some energy inside your system to reconverge to a good state. Okay? But it is, of course, not perfect. But it was possible to maintain your system at 3, 4, or 2. So you are in a range between these two things in general. Bon. What time is it? I have 20 minutes. Okay, that's okay. So let's continue to autonomous feedback or coherent feedback. So you have different things. Autonomous feedback, it is, okay. So, and go to an autonomous feedback, in fact, that we can imagine also for the photon box. So you don't need to measure something, but just what you have to remember the scheme, you have a reservoir of atoms, okay? that are prepared in a slightly excited state. Of course, the atoms should to have some energy to compensate for energy lost. Okay, so you inject atoms which are slightly excited. So you can put them slightly excited, you know, by the first Ramsey pulse, okay, from the preparation box. And then you tune, in fact, the interaction during the passage of the atoms between the two mirrors and the interaction with the photon. You tune the interaction in 3 zones. Okay? It is a composite interaction. Composite interaction. Essentially, what you use is you use a Stark effect. So you put a different potential between the two mirrors to have a constant electric field. that shift, in fact, the energy between the ground state and the excited state. Of course, the photon, they don't care about the static electric field, just the atoms, the Rydberg atoms. So, which means that what you do, so here you recognize here the James-Cumming Hamiltonian, where you have the frequency of the cavity, the frequency, in fact, of the atoms, and here you have the Rabi frequency here, omega. And what you can do is this. So assume that the passage through the atoms, this is the time, t, okay? So I assume that at time t is equal to 0, the atom is just in the middle of the cavity, okay? And here it is omega q. And here I have 0, I've put 0. So omega q is first dispersive, typically blue shift, with respect to the cavity. Here you have omega c. Okay. Then, during a small zone, it is exactly resonant with the cavity. And then you use exactly the same step, here delta, after this. So it is here blue detune, it is red detune, but exactly symmetric. Okay? And you can do this just by changing, in fact, the electric field during the passage through the atom through the cavity. In this case, what you have, if you tune correctly the parameter, of course and then the atoms get outside and crash on the wall of the cryostat. Okay. You don't care about the atoms. So you trace over the atom that has interact with the cavity, and you obtain a Krauss map. And here I have a small, in fact, illustration of what's going on when you tune correctly the parameter of this. And this was an idea of Alain Sarlet. And here it is the Wigner function of a photon inside the cavity. So here you see the number of atoms, and it corresponds to something which is not completely realistic. So take into account, in fact, the finite photon lifetime, some typical things, okay? And what you see is that you converge to, in fact, something which look like, with some distortion, to a Schrödinger cat, because we have taken into account some, this is an approximation, of course, but we have this. Okay, and so it is called reservoir engineering, and I remember quite well when we discussed this with Jean-Michel Raymond, and then Serge Arros came, and he looked at this, it is, oh, that's interesting. It is not control, it is physics. Okay, it is physics. It is not control. So, and they do not have performed this experiment because it's something which is not very easy to do in their setup, this kind of things. Okay. Well. So, to have an idea of the proof, okay, it is here, it was in the thesis of Zaki Lektas. We just have to, we perform, in fact, a change of frame where H is a kind of Kerr Hamiltonian, so it is a function of N. And in this Kerr Hamiltonian, we can prove that, in fact, you have some assumption that we converge to, in fact, a pure state. And if you tune correctly the parameter, this pure state is close, in fact, to a coherent a cat state. But at the end, it is here. And if you are interested, look in the thesis of Zaki. Oh, so I will not detail this. But you see, you need to find the good frame, and then to have some, you see, theta for all n, and you have this thing and all this stuff. So at the end, what is the trick of reservoir engineering and these things? So you have your system. You assume that your system is perfect. You have your controller, okay, which is a passive, in fact, DC passive system, and all the things is to engineer correctly the interaction. Okay. my system was the photon, my reservoir was the reservoir of atoms that are reset at each time. So it is the environment, of course, forget its initial condition because I reset. Okay. Yes. So if you do something like this and you find an interaction Hamiltonian such that your system converges to typically the pure state you want into your system or to the code space, okay? In this case, it is something which lives on a manifold, submanifold of H, okay? And here you have something in the reservoir, and it's converged exponentially at a rate, in fact, 1/2. Then you can assume that if you put some errors on your system, by robustness, you will converge to something with some mismatch here, but the mismatch will be small if the convergence rate with respect to, in fact, the decoherence rate, okay, dominate. It's something. So you need, it is important to have this convergence rate and so on. Okay, that's in fact the philosophy, I will say. I say nothing, but it is important to have this. And for that, what we have is we have to study, in fact, the master equation of a closed loop system. So you have a lot of property of this, and in particular, this equation is always a contraction, but it is in with L1, I will say, distance, not quadratic distance, in fact. And the trick to prove, in general, is to find, so you have your system, and the trick is to find a good operator, Hermitian, which is positive and which vanishes at the goal. And such that when you compute, in fact, its derivatives, okay, which is its derivative in the Heisenberg point of view here, you obtain a symmetric Hermitian system, which is negative, okay, which is negative. So in this case, you decrease. It is Lyapunov things. This thing. Okay. So, and now I will speak a little bit. So, what time is it? Yes, I have. Yes, I have time to explain what's going on for the cat qubits. Okay. So maybe I am a bit thirsty. So for the cat qubit. The goal is to converge goal is that rho system should be converged to the span of a coherence state alpha and a coherence state minus alpha, the code space. So you want to converge to that. If you are not on the code space, you want to converge to a code space. Okay? So it is not here, but it is instead of converging to a pure state, you converge to, in fact, a code space. But it is more or less the same. Okay. And then what you have, it is known since a long time. If you take as dissipator, but only on the qubit, okay, on the photon, if you use this dissipator, where L is typically something which is loss of 2 photons, photon by 2, minus alpha 2 is identity. Then you can prove this. I will do a computation. You take this master equation and you have this. So I take L is equal to A2 minus alpha 2. Here it is identity, of course. What I have to compute is I have to compute d over dt here, when I take my Lyapunov function is L dag L, I take A is L dag L, and I want to compute d of A. So this is exactly, in fact, the adjoint dynamics of the, in fact, Lindblad dynamics. So what it is, and you can always write it like this, it is LDAG, this formula, it's important to do the computation. AL plus LDAG AL, you have a bracket, and you divide by 2. So I have to compute AL. What is LL? It is LDAG L, L. But this bracket is a derivation, so I can first derive with this and with this. So it is LDAG L, L, L. So with this guy is exactly the same as this one. So it is what? It is LDAG. Here I have a bracket of LDAG L, and here I have L. You see, if I show that this guy is negative, it's okay. And what is LDAG L? It is ADAG square A. So it is, I derive by this, it is ADAG A2, ADAG plus ADAG, ADAG A2. What is this? This is minus 2A, and this is minus 2A. Okay? So at the end, what you obtain is something like this. LDAG L, it is minus 2, and here I have something, I have ADAG plus ADAG A. So this is N, this is N plus 1, so what it is minus 4N minus 2, okay? And from this, okay, you obtain this. The 2 come from this, you neglect N because it is bounded by 0, and you obtain this thing, and you know that at the end, the trace of LDAG rho L converge to 0, which means that, in fact, okay, which means that rho infini, what's going on at the end, rho infini, it is in the space alpha and minus alpha because of this, which means that care of rho k, no, support. The support of rho k is included in care of L. And what is care of L? Since L is equal to this, it is plus or minus alpha. Okay? Voilà. At the end. So I will not detail this, but it is this. So you have a Lyapunov function, you converge, and so on. Okay. But of course, it is not obvious to design this kind of stuff. So it changed photon 2 by 2. It's not so simple. So, and the trick is that you can design something like this, but in an approximate way. So it was, in fact, an idea of Zaki Lektas and Raphael Lescan. And here you have also Theo Perronin. So they have founded Alice et Bob after their PhD thesis in the group. It was with Perronin was with Benjamin Huard, and Raphael was with Zaki Lektas. And you see here, you have your composite system. So this is your system. So as, in fact, David said, it is a LC oscillator in superconducting circuit. Okay. It is capacity coupled. With this capacity is weak. And here, what is called asymmetric squid, okay, and your control, here you put the control corresponding to external flux. So you have an LC oscillator and you shunt it by 2 junctions. So I will not enter into the details. You have, in fact, the modeling all these things like this. And what you do is that you have 2 external flux. You have average flux and the average difference, okay? The sigma and nines and so on, and you do something like this. And here you have dissipation. You have a kappa here, and you assume that your system is not too dissipative. And in this case, this composite system, you need transformation and so on, rotating wave approximation. At the end, it has this form. And you tune correctly the interaction between, in fact, so you see, you have B, the B mode is as frequency omega B, the A mode is as frequency omega A. So you need to put some 2 omega A minus omega B, in fact, to preserve, in fact, the energy exchange, okay? Which means that in these things, okay, you see, so it's a kind of, you see, a kind of James-Cumming Hamiltonian here. When you gain 1 photon in the cavity, you lose 2 photons, in a certain sense, in the controller. You gain 1 photon in the controller, you lose 2 photons in your system. But you have a drive. But here, the alpha 2 is just a drive on B. Okay? But you can put it there. And here you have the damping of B. So you can prove easily that on this system, any state where B is in vacuum and grosso modo A is a superposition of alpha and minus alpha, okay, is a steady state of the system. Oof. Okay? And then to prove, in fact, the convergence, what you can do is to use what is called, I will say, a singular perturbation in or adiabatic elimination. So your system here, you assume that the G2, the coupling parameter, is much smaller than, in fact, the kappa B. Which means that what dominates your system, it is just the loss. And here it doesn't have time. So in your controller, the photon, in fact, escape very rapidly. Then in this case, you can use what is called adiabatic elimination. You neglect, in fact, the dynamics in your, it is your reservoir here. So which means that in a certain sense, you neglect the dynamics in your reservoir. So you forget very rapidly its initial condition, but you have to take into account its influence, but at second order. You need second order perturbation here. And in this case, you recover at second order your ideal case where your dissipator is A2 minus alpha 2. Okay. So you see in this case. So for this, you can have a perfectly mathematical proof of this. It was in this paper, but to prove that this system converge always to, in fact, something on the code space, we do not have a Lyapunov function for this. We have a recent paper for this, but this is something which is, I will say, a huge, in fact, functional analysis machinery to prove that. It's something which is not very simple. But we have a proof that whatever the initial condition is on this system, you asymptotically, you converge to this. We do not have exponential convergence as here because of Lyapunov things, but still we have this. So it is just for, they don't, of clear experimentalists don't care about this proof. Okay, they don't care at all. But I think it's interesting to develop mathematical tools for that. Well, and I will conclude here. It is why it is interesting to have cat qubit. I will not enter into the details, okay? And then I will conclude by this. So you can mix both to protect quantum information. Here you have something which is local controller, almost quantum. In fact, to stabilize the fastest, in fact, error degree of freedom that you can do. And then through quantum measurement, because you have to measure something, of course, to see what's going on in your system, maybe you can, in fact, you have time in this case, okay? So you do not bother about feedback delay in the feedback loop, And then you can typically do auto-tuning, auto-calibration, and some resetting and so on by some, in fact, a classical controller, something like this, okay? And it seems to me, but it is a case of a strategic view, you know? You need to have a strategic view nowadays, always. Our strategic view is to rely on the stochastic master equation, which are widely used and that are easy to manipulate. If you look at the way we formalize it, we explain it, and for each system, you have to develop adapted mathematical and numerical method to increase the precision in the modeling and in the control of the system. Okay. Voilà. And at the end, of course, I am not alone, okay? If I can do this lecture, it is because I have the support of all this young generation. Here you have Maziar Miraimi. You can hear Antoine Tillois. Pierre is here. You have Philippe Campagne here, Ibrak. You have Zaki Lektas, member of the group. I'm looking, where is Alain Sarlet? You see it here, it is here, Alain Sarlet. Really, what is quite nice is that you see me always. You see, it is the old guys. But all the other guys, it is difficult to make the difference between the student and the permanent guy in the group. So it is nice. For me, at least it is nice. I am protected by a gap of 20 years. Okay, I finished. So thank you.
Okay, so we have time for questions.
Can you show the schematic again of the experiment? The schematic where the cavity and the you had this.
Yes.
Yeah. So in the actual experiment, when you do the control, so that's through that phi, right? So yeah. What exactly do you do in the experiment? You said you send a pulse.
Yes, it is a pulse. So it is. You have an antenna. It's something which is with the same technology that you have in your cellular phone, and you send a pulse during a certain time with a certain phase and amplitude. The phase is always 0 pi. We need only alpha, so the current displacement should be real. Everything is real here. Okay, you don't need a complex number. But the phi here, it is 0 and pi, and you have to decide. So you have a sort of just I push positive or negative. Okay, it is this, and it is just an antenna, and you inject a lot of, in fact, classical coherent photon toward the cavity. And since the cavity is slightly open on its edge, okay, this pulse has, in fact, this coherent photon pulse acts as a coherent displacement, okay, on the photon inside the cavity. Of course, there is a gain between the amplitude that you put in your electronic device and the final amplitude that you have on the pulse inside the cavity. Okay? You lose most of the energy that you have sent toward the cavity, in fact, and you have only part of this energy is capped by the photon.
But you want to control the interaction with the atom and the cavity, right? How that's why I thought you wanted to, you had that cos of n theta.
Yes.
And you wanted to change that, right? So with this,
what will we change?
So the UK that you want to change, UK is what you want to control.
Yes, U is phi and A.
Right. Yeah. But finally, you want to control the interaction between the atom and the cavity.
No, right? No, we don't control the interaction.
Okay.
We just put it is a local control, this, on the cavity state. So, okay. And you put, of course, you inject this when there is no atom between inside the cavity. Of course. Okay. Of course, the guys, it is misleading here. The atom has passed, you put a pulse, and then the next atom enter. You never put a pulse when in fact the atom is inside the cavity. Of course, it is a local control. Okay.
Yeah, I have a question about, so your feedback depends on the filter you compute.
Yeah.
Is there any ideas that, because I guess it takes sometimes, you need to compute it in K here, I guess, in the computer K. So is there any idea of design that would just don't use this filter, but directly try to do some feedback using the outcomes of the measurement?
Maybe there is something, but we don't. So outcome is 0 or 1. And Markovian feedback, you say, with you. I don't see what.
Not necessarily, I mean, then it should depend on the whole sequence of measurement, not only the last one, I guess.
Yes, maybe. But what is bad in this actuator is that even if you are, for example, at 4 photons, you want 3, the coherent pulse will give you off-diagonal terms. And you need to measure to go back to the diagonal, to kill this coherence to reconverge to a photon number. But it is this measurement process is not deterministic. So you have to see if this measurement during the time tends you to go to 3 or to 5. Okay? If it goes to 5, you have to put another coherent state. Okay. Because the actuator is not well adapted to the goal. Okay, and you will see in the lecture note, I present something which is much easier. It's when the actuator, in fact, it is you remove all this thing, and the actuator is just, in fact, saying that the probe atoms, it will be also controlled. Either I send an atoms, which is in fact QND to measure, or I send an atoms that can remove 1 photon, but in this case, this atom will be resonant, and either it will enter in G, then it can in fact catch 1 photon, or enter in E, then it can put 1 photon. And then your control is completely discrete. U is equal to 0, it is QND atoms. U is equal to -1, it is, in fact, atoms entering in G, but with resonant interaction. So you tend to decrease the number of photons. Or the atom is in E, and you tend to increase the photon. And in this case, you do not need quantum probability. The dynamics is always on the diagonal in this case. So just, you don't need to have in your controller, in fact, this of diagonal terms. You remain on the diagonal in this case. And it was much easier. They done the experiment 2 years after. Okay, they put a paper, very nice one, using more or less the same Lyapunov function. Okay, but with typically the atoms that could be also a controller. Okay, and it is much more adapted to what you want to do. Okay, but it is no more a quantum probability. You can do this with just a classical probability. Here, you need quantum probability to take into account this coherence, especially during the burst here that are here. Okay, it was not possible because the actuator has limited capacity. And it is the combination of displacement and measurements that you can combine them to achieve your goal.
There's another question there on the side.
Hello, Pierre. Thank you very much for this lovely series of talks. So I'm still trying to digest basically the convergence analysis that you've presented. So could I just ask you the following question? So the little bit of quantum control literature that I've studied, the design of the controller, so so the task is presented like you have written on the wall that the goal is, for instance, to stabilize cat states.
Yeah.
And then what happens is that, so it seems to me that the design of the controller or the feedback Lindbladian or the feedback Hamiltonian is basically algebraically designed. So you think about Hilbert space, you think about kind of, stabilization, so on and so forth, and you design it. I have not seen, so my question to you is, I have not seen carefully enough spelt out the convergence analysis creating, making an important role in the decision. So it seems to me, and I'm convinced by what you're saying and from the lectures, that this is indeed the case, but I'm not yet able to see an example of it where it really becomes very clear to me. So could you at least just talk to us about where, for instance, you would try and design a controller looking at the Lie algebra, but then the convergence analysis leads you down to a more subtle conclusion than just the Lie algebraic conclusion?
So it is here. The Lie algebra is here.
Yes.
Yes, in the computation of a Lyapunov function. Okay?
Yes.
But the trick is to do why taking this? Because I do the computation. It is as usual. So either you, somewhere, even in control, you need some algebra, in fact.
I agree, yes.
To do this.
Yes.
What is the most important? Algebra or analysis? It's both.
Sure.
I will say.
Sure.
In this case, what is important, it is this. So where is it? It is the fact that what you have at your, so you know your system is this, and assume that you have an Hamiltonian, which could be 0. Okay, and you want to stabilize inside the Hamiltonian. Okay, HS could be 0. You are in the frame rotating at the Hamiltonian of your system. It's typically what's going on in an oscillator. You turn at the frequency of a system. So H is 0, of course, and here you have your controller. Your controller, so you need to have at your disposal, okay, something which is dissipative, and where you can control at least the dissipation channel, 1 or 2, or the strength of this dissipation channel. And then what you have is, this is physical device, and then what you have to tune an interaction. And here, as far as I know, either in quantum optics or in superconducting circuit, you cannot use any, in fact, interaction Hamiltonian. Of course, if you have a degree of freedom choosing what you want, it's not very difficult to adjust the algebra to get what you have, okay, to get this. The problem is that you are playing Lego, but with very specific blocks. And how to arrange them? To arrange them, you need some algebra, and typically commutator, like this. But you need also some intuition and so on. So it is the geometry. So what is important, geometry or algebra? To get intuition of what's going on.
Sure. You're saying, so you lead the design on the basis of geometry or algebra or whatever, but then you check the convergence by doing the calculation.
Yes,
okay.
Yes. You need to have, in any case, I guess it is important, at least for us, from a mathematical point of view, to have what is the pure case. And on this pure case, there is no ambiguity. I don't need to do some simulation. I have a mathematical proof, so it is okay. Now, the reality, you have this, you assume that your pure case is something that you guess the essential, the main part of what's going on in your experiment. But it is not sure. And in general, it is a feedback process. You have an idea, you say the ideal system is this. You see that in simulation, it is not very robust. If it is robust in simulation, you try to find an experimentalist to do the job. You say, well, it is completely realistic what you propose for that or that, and it is an iteration process. So that's life.
Is there any other further question? If not, I think we can thank Pierre again.